Professor Harish Dixit is an associate professor at the Department of Mechanical and Aerospace Engineering at IIT Hyderabad in India. His research interests are in dynamics of drops and bubbles, thin films, and vortex dynamics. So I welcome you, Harish. Floor is yours.
Yeah, thanks, Vagesh, and I thank the organizers for giving me this opportunity to share some of the work that we have been doing the last few years. This is work with my former PhD student, Praveen. I also have to thank Jacques for accepting our paper, because he was the editor associated. He was the editor who handled our JFM, and he accepted our paper. So you will see some of the work from the paper, from the JFM, and another physics of fluids paper. So I'm primarily interested in asking what is the role of gas cushion during impact of a drop. And if you in the previous talk, Jacques was talking about two bubbles which come very close to each other. So that's the kind of scenario that I'm interested in this problem. What happens when a droplet comes very close to either another droplet or a plate, a solid surface? So in this particular talk, I'll only talk about droplets interacting with solid surfaces. So this problem actually has a very long history, as all of you know. This started with Worthington's work. Actually, it was a talk actually in 1895. And I find this fascinating because even today, it's very challenging to get such beautiful images. And I think one of the things it's also very beautiful. Therefore, he himself observes that it's an exquisitely regulated phenomena, and it's a very complicated phenomena, and it's a very, very active area of research. I think in APS meeting, for example, drops and bubbles are you'll find large number of parallel sessions on it. And just in the last sort of 15 years, there have been at least, I think, 5 or 6 annual reviews on it on various aspects of impacts. Okay, so this is another very important paper which summarizes various kinds of impacts that you see. This only focuses on droplet impacting solid surfaces. Or you get the more favorite ones for a large number of people are usually these splashing regimes. And there's been a lot of intense research on these rebound problems, and that's one of the things that we'll focus as well. And the entire our work is completely focused on the complete rebound phenomena. So this happens usually for when the droplets impact hydrophobic surfaces. In fact, almost always superhydrophobic surfaces. The scenario, the popularity of this research, in some sense, the field itself was turned upside down by this very famous experiment from Sid Nagel's group in 2005, where they showed that the surrounding gas has a very, very important role. So here we see droplets which are impacting the identical droplets are impacting the same surface, but the only difference is the surrounding gas pressure is reduced. And as you do this, the phenomena completely changes. Here you see clear splashing, and then you see absolutely no splash. So they observed that reducing gas pressure can completely suppress splashing. And this highlights that the surrounding gas has a very important role in what happens during impact. And this is I think I have to switch to, yeah. So let me just play that again. So here, the same movie from their paper, Sid Nagel's paper. In the top, you see this splashing phenomena, and at the bottom, splashing is completely suppressed. And so the question, and this led to a lot of intense research on what's happening during the contact just before impact. And this is work from Mahadevan's group and actually Rubinstein's group. And so what you're seeing is a drop which is actually impacting on a hydrophilic surface, and the same phenomena is being imaged from the bottom, and you see this gap that is being imaged from the bottom, and this is a gas cushion. It's more clear when we look at another work from a group in Netherlands, where they showed that when you actually have a droplet that undergoes multiple rebounces, I'll play that again, and notice here at the bottom that you see these interference fringes that form. And these fringes are actually highlighting that there's actually a gap between the droplet and the solid surface. In both these cases, the surface is actually hydrophilic. not hydrophobic. So this shows that you can actually have rebound even on a hydrophilic surface. But of course, in the case of hydrophilic surface, the drop never touches the surface. Okay. And in both these cases, a thin gas cushion prevents contact and even causes the drop to bounce. Now, of course, there's a catch here. In both these cases, the gas cushion is very thin, usually of the order of microns, and therefore the surfaces have to be very, very smooth when you do these experiments. This is another very famous work where it showed that drop bouncing, drops can bounce on hydrophobic surfaces repeatedly multiple times. And by basically, it's almost like a tennis ball which is bouncing on a surface. And therefore, from the way the trajectory of the maximum height with time, you can actually, this is a compound image, you can actually estimate the coefficient of restitution. And these are for very small, very high contact angles, and the restitution, the contact time is very, very, very small. So therefore, the authors concluded that viscous dissipation during contact is basically negligible. And all right. So what's the subject topic for our interest? We want to understand what's the role of Reynolds and Weber number. We also want to understand what is the role of the underlying gas layer in energetics of impact. So this is the kind of scenario that we have. We release a droplet from a certain height, and the droplet, depending on the Reynolds, especially the Weber number, it may undergo oscillations or it may just remain spherical. It comes and makes contact with the surface. And in almost all our cases, the droplet remains nearly spherical because we are looking at lower Weber number. I'll come to that. And then it spreads on the surface. And when it spreads on the surface, we want to examine what happens in this thin layer. And notice that I'm only highlighting one side of the surface, solid surface. That's because we do axisymmetric simulations. So this is the kind of this little region here where the drop actually is spreading on the surface. That's how it will look. This is an actual image. And these are the velocity profiles extracted from the simulations. We have a gas layer, which is, there's a velocity gradient in the gas layer, which leads to a lubrication pressure and which supports the droplet. And so the work is actually published in these two papers, one in JFM in 20, actually this is, I should have corrected this. This is 2021 and the other one is in 2020, last year. Okay, so the setup is as follows. We have an axisymmetric droplet, which is released from a certain height. And we fix the viscosity. All these parameters are fixed such that it's an air-water system so that we can directly compare our simulations with experiments. And we have done a few experiments, but I'm only going to show one video from our experiment. All simulations were carried out in Jeris, and we've started doing some of these simulations in Basilisk, which even Jacques was talking about in the previous talk. And we use the volume of fluid method. There's a very well-developed solver for these kinds of problems. So first, let's look at the easier part of the problem. The easier part is to match the shape of the droplet. That's something that we have to do to make sure that we are validating our simulations. I call this easy because even though this is actually reasonably hard, it was difficult to achieve. The next part of the work was even harder to achieve. So what we do is we make sure that our simulations are accurately getting the shapes that were reported in experiments. These, as you can see, these are low Weber number experiments, and the drop remains nearly spherical just before impact. And the yellow curves are the simulation shapes. And but we are also interested in making sure that we get the gas profile reasonably well. And I say reasonably well because we are talking about gas profiles in the order of microns, but the droplets themselves are the order of millimeters. So straight away, we have a ratio of 1:1000 when it comes to the thickness of the gas profile vis-a-vis the droplet. So these are very intense as far as numerical simulations are concerned. And just getting the overall shape itself was quite challenging. But I think with the newer set of simulations that we're trying to do, I think we hope to improve some of these things. Jeris also has a few limitations. For example, Jeris is an incompressible solver. There may be mild compressible effects, but we cannot capture that. But notice that we are able to get the solid lines are basically the experiments, and the dashed lines are our simulations. We're more or less getting the same, the minima that we get in the gas profile thickness, we're able to get that. We're also almost able to get the same number, and the refinement here is very, very high, which is what makes these simulations very challenging. Okay, so we actually can see three scenarios which were observed in simulations and experiments, but not so much in lubrication-based theories. And I'll talk about these scenarios. So first possibility is that the drop can actually come on the surface, come close to the surface and spread on it and be supported on a gas cushion. Now, it could make this could be the sort of the shape of the droplet. Now, these minima that you see here, this is where the gas can completely get eliminated and drop can make, so here it can have touchdown over here. So this is one scenario where you can actually have a contact of a droplet with the surface, and you'll notice that there is a gas bubble, a large gas bubble, which is entrapped. There's another scenario which is also reported in experiments, which is that the drop actually traps a very, very tiny bubble right in the middle, but it also has a minima away. But the contact does not occur at the outer minima, but it occurs at the inner minima. So the first scenario where the drop never makes contact with the surface, the nature of the surface is independent. As the wettability of the surface is unimportant, so we call it wettability independent regime. And where it makes contact, what happens subsequent to contact depends on the wettability of the surface. So we call it wettability dependent regime. Okay, so we first conduct a large parametric study. We find out when do we have a thin gas layer and when do we have contact in the simulations. There is a bit of a difficulty in determining an exact boundary where drop makes contact, because we have these difficulties that Jacques was highlighting in his previous talk. When the region becomes very small, the thickness of the gas layer becomes very small. Sometimes we have one cell in the simulation. We keep refining it, and we basically have a cutoff where we say that below this thickness, we say contact has occurred. So therefore, these are basically, we can vary this. If we refine it further and further, then the Reynolds number at which contact occurs can be pushed higher. So we are not very sure about the exact boundary, but we can be sure that these regions, in this region, we do have a wettability independent bouncing, meaning we have a gas cushion. That's because the thickness of the gas layer is close to a micron. Okay, so, and we also notice that there is sort of a peak, an optimal value of Weber number 2, where basically we can ensure that droplet gas cushion, the drop can be supported on a gas cushion for a wide range of Reynolds numbers. Okay, we look at a few cases. I've randomly picked 4 different cases. I'll quickly run through them. So the first case is a low Weber number case, and you can see that because of low Weber number would mean that surface tension is strong, and therefore it remains nearly spherical. And when it remains nearly spherical, the droplet actually comes on the surface, spreads, and gently rises back. And as you increase Weber number, now you see more capillary oscillations on the surface of the droplet, and that is also evident here. These are 3D views of the same thing. Weber number 1 and 3, you see these capillary oscillations as you go close to Weber number 1. And at Weber number 3, you see that the upper surface of the droplet capillary waves get focused here, and you can actually have a very nonlinear oscillation of the wave, and eventually it plunges down and it can entrap a bubble at some point. And we also notice that the spreading phase of the droplet, it's exactly like a tank treading motion. That was also reported recently from various groups. And this is exactly what I was talking about. The droplet actually comes and spreads on the surface. The blue curve is the initial shape of the droplet. And the red curve is the initial shape of the droplet, and the blue is the final shape. And then this is the receding phase. It starts with the blue and then goes back to red. Okay. So based on the shape of the droplet and the gas film below the droplet, we can actually identify a few sub-regions. So in the first region that I've highlighted here, the contact, there is no contact, but the minima occurs on the outer region, outer periphery. So we have this sharp minima. It has been shown that if you actually do these simulations or do the theory without surface tension, then you actually get a singularity, curvature singularity here. And if you increase the Reynolds number, this minima eventually makes contact with the surface, and you actually have this regime 2. So the contact occurs at the outer periphery. And in the regime 3, 4, 5, the minima is in the center. So here I'm looking at the gas layer all the way here in the small rectangle here. And I'm showing the region here. And there could be a small dimple, another dimple, and very close to the center. And I'll show better images of the gas shape. So here's what I'm showing 2 examples. So this is basically the shape of the gas cushion. So here is the gas, and here's the droplet. And you can see that for high surface tension cases, it spreads gently, and you have a minima in the outer region. But as you keep lowering the surface tension, that is at a higher Weber number, then you have this a very flat region, and this flat region can actually dip downwards and make contact with this near the inner kink or the inner minimum can make contact. All right, so that's basically the various regimes that we have this classification. And I'll quickly move into energetics of impact. Now, when it comes to energetic impact, so what we are really doing is we are releasing the droplet at a certain height. That's, let's say, h naught, and it comes close to the surface and then bounces back. Now, this is a case where in both these cases, whether it makes contact or no contact, our simulations are done for superhydrophobic surfaces. So in both cases, it undergoes a complete bounce. And the droplet basically rises up to a new height, which we call as H1. And depending on the Weber number, if the Weber number is very low, which means that it remains nearly spherical, there it is as close to an elastic collision as possible. But as you increase the Weber number, a lot of energy is lost to surface oscillations, and therefore you actually the height at which it rises is very low. Now, Reynolds, this is largely a surface tension, capillary oscillation mediated loss, not a direct viscous loss, because if you repeat this for a fixed Weber number but vary the Reynolds number, the height to which the droplet rises does not change too much. So here this is a sort of a busy slide. And what we are doing here is we are looking at various energies of this, various energies that we're looking at, starting with potential energy and kinetic energy of the droplet. And on the right side, we're looking at surface energy and the total energy. This is the energy lost due to dissipation. And I'll only focus on a few basic points here. As the droplet, this is the x-axis is time. As a droplet descends, its potential energy reduces with time, and its kinetic energy correspondingly increases. And once the droplet is at this lowest height, the surface energy, notice that during this process it remains constant because it's a spherical droplet, and then the kinetic energy decreases rapidly and the surface energy increases at the expense of the kinetic energy. And then after that, when the droplet eventually rises up, takes flight again, the surface energy and the kinetic energy exchange are completely out of phase oscillations, which means that they're exchanging energies. This is actually one way in which you can actually have an energy loss. You can have energy loss not only during contact, but you can also have energy loss during flight because the surface oscillations are generating a large amount of motions inside the droplet. And so this is a few cases that we notice that there are a few jumps here that we see here. Those jumps occur because when the droplet actually falls on the surface, so here it basically traps a bubble, and this is where you actually have a big loss of energy because of these violent motions. And in the second jump that we see here, the bubble which has formed eventually escapes, and that generates a lot of shear and it generates a lot of kinetic energy in the gas, and therefore some drops energy is actually lost to the gas. So we not only look at exact shapes of the droplet, we compare our energies, the restitution coefficients that we get from reported values. So for example, what you see in the brackets are the experimental values, and the numbers outside are our simulations. And you can also, the yellow region shows that the restitution coefficient is very high, whereas in the blue region, the restitution coefficient is very low. This is one of the things that we wanted to answer, which is that the Mahadevan's group, the Kolinsky et al., they had reported a very low value of coefficient of restitution, whereas Reuter et al. Had reported a much higher value. And these were seemingly very similar experiments. And these were done almost parallel to each other. And therefore, we wanted to understand why are the numbers so different. And we noticed that they're now very different because they're in completely different regimes in this diagram. Okay, we'll quickly run through a few scaling laws that we've looked at. Now that we've looked at energies and the shapes of the droplets, we can ask a bunch
Harish,
of questions.
Sorry to interrupt. Would it
Yes.
be possible to wrap up in a minute or so?
Yes, almost done. Okay, so I'll quickly go to maybe one scaling law. So we've looked at, we can ask a bunch of different scaling laws. We can ask what is the height of the droplet just before contact, what is the spreading radius, what is the minimum thickness of the gas film, what is the radial extent of this kink, how long does it take for the droplet to rupture, and what is the energy loss during flight, and so on. So I like the general way we derive the scaling laws is to look at lubrication approximation. So here's the lubrication approximation of the gas film. Now we can write down the lubrication approximation. We have three terms here. The blue is basically the capillary pressure. This is the gas pressure, and this is the capillary pressure, and this is the inertia. And we can do a balance of these things. And in the high inertia limit, we have a scaling law which scales as Stokes bar minus 2/3. And the low inertia limit, we balance the gas pressure with the lubrication pressure with the surface tension, and we get a different scaling law. And this is a comparison of the scaling law capillary power 1/2. These are all our simulations, and the solid symbols are a few experiments. And by and large, we managed to get a fairly good agreement with the scaling law. When it comes to the radius of the kink, we again do a balance of the pressure of the gas layer with the weight of the impact force. And by doing a balance of this, we can show that the kink, the point at which the minima occurs, goes like Weber power 1/4. And I'll skip the radial extent, which was done by David Carey's group. And the radial extent of the gas film is like this Weber power 1/4, which is our simulations. And the solid ones are data that we have extracted from experiments. Again, this scaling law does fairly well. The time of rupture depends on the regime. If you're in a regime where contact occurs on the outside, we have a different regime. That's we call it as regime 2. And if the contact occurs in the inner region, then there is hardly any lubrication pressure to support it, and therefore we get a very different. The time of contact does not depend on the Stokes number. Stokes number is a proxy for viscosity of the gas, and we can do a similar thing for the dissipation. We can write down the general expression for the dissipation, and we look at the dominant balance. And here we can see shear in the gas layer. And by looking at the dominant balance, we can actually get a scaling law for the dissipation in the gas layer during contact. So this actually tells us how much of energy loss, how much of the drop's energy is lost to the gas layer during this process. And this is a scaling law, Weber per half and Stokes per half. We do two different ways of checking this. We vary the Weber number, or we vary the Stokes Reynolds number or the Stokes number, and we get a fairly good agreement in both the cases. So I'll stop my talk here, but I'll just quickly highlight what we have found. We've looked at the role of gas cushion in great detail. We've looked at phase diagrams in the Weber number, Reynolds number plane, where we distinguish when contact occurs and when we don't. We've also looked at the energy budget, and we find that more than Reynolds number, it's Weber number which is far more critical in these experiments, because Weber number dictates how violently the drop oscillates. And we've looked at a bunch of different scaling laws. Some of these are not, all of them are not new. For example, the scaling law for X, which is the maximum extent of the droplet spreading, or the scaling law for minimum thickness of the gas layer were already derived in literature, and a few of them are new. So with this, I'll stop, and I'll be happy to take a few questions.